Trigonometry, the field of math where people decided to put a bunch of lines and a triangle inside of a circle. Well, what if we wanted to go further than this? Today we're going to do tons and tons of trigonometry. Try your best to understand the basics. This is going to be weaponized middle and high school math. At the end, we're going to define all of these out of 4's. More on that later. I shamelessly stole that image from Wikipedia, and as you can see here, the complexity is going to escalate extremely quickly. We literally just start with the circle and 2 points. One will be at the origin, the other will be at 1, 0. We place a third point on the circumference of the circle. We don't really care where it goes. Now we have an angle, and we also have 2 radii to go with it. Nice. They're going to be 1 unit long since this is a unit circle. For some reason, when naming things, math likes to use the Greek alphabet a lot. For our purposes, we're going to use theta. So when we take a function of theta in radians, we're going to map that onto some strange number. Sometimes it's a complex number, sometimes it's not a number at all. Here are the respective equations. As you can see here, there are tons and tons of trig functions that will be covered today. These are the ones that Desmos will let you use. These are the ones that DeepSeek knows about. These are the ones that you probably already know about. These are the ones that are covered in this video. Be warned, there's a little bit of swearing. These are the ones that he made up in that video. This is the one that I made up. Yay. Now that we have a pizza slice, a circle, and theta, let the anarchy begin. So we're going to start off with sine and cosine, which we just drop a perpendicular onto the other radius. And we have 2 more segments. There's technically a third segment here, but we're going to ignore that temporarily. Anyways, you're probably already taught this. Yeah, they're just the legs of a right triangle, and cosine can be defined using sine. Here we have a sine and cosine wave overlapped on each other. Yay! Also, cosine is just sine shifted to the left a little. This will be very useful later. Also, we can figure out where the third point is with coordinates just using theta, cosine, and sine. It'll be at cosine theta and sine theta if we know theta. If we don't, then good luck. Anyways, tangent is the length of the glowing segment. You were also probably taught this. It's literally just sine over cosine, or sine, yay. Also, in a right triangle, sine, cosine, and tangent will give you ratios when given a certain angle. Also, when you take the tangent of 90 degrees, it will kind of give you an error. When you take inverse sine, inverse cosine, and inverse tangent, you input a ratio and give an angle. Yeah, not much to say here. Anyways, you can define these with each other. Here they are. Yippee! Next up is cosecant, secant, and cotangent, which are the reciprocals of sine, cosine, and tangent, respectively. And then we have the inverses of those, which can be defined with more inverse sine, pi, reciprocals, blah blah blah. Next we have the hyperbolic sine, cosine, and tangent, which we have to use Euler's number for this for some reason. And it's basically the same thing as sine, cosine, and tangent, except for the fact that we're using a hyperbola instead of a circle. That's what Wikipedia says, and I still don't understand it. Anyways, we have the reciprocals of those, cosecant, secant, and cotangent. Yeah, the hyperbola strikes again. Now brace yourself for these next ones. We have inverse hyperbolics now. We have sine, cosine, and tangent, inverse hyperbolic. We have the natural log. Very nice. Next we have inverse hyperbolic, cosecant, secant, and cotangent. More natural logs and more reciprocals. Next we have the versine. That's the segment that I alluded to earlier. It's literally just 1 minus the cosine, defined using more sine. Yay. Anyways, hyperbolic versine. Yeah, more hyperbolics. I don't understand this. It's hyperbolic cosine minus 1, more Euler's number, blah blah blah. The verb cosine, we literally just swapped. I think we just swapped the prefixes, but whatever. 1 plus the cosine, blah blah blah. The covert sine, yeah, this is where we swap them. 1 minus the sine, not very interesting. Then we have the hyperbolic covert sine. 1 minus hyperbolic sine, more Euler's number. The covert cosine. Yeah, there's a lot of these guys. We have 1 plus the sine. Yeah. Next we have the Haber sine is the length of the versine, but half of that. 1 minus cosine over 2, blah blah blah, more sine. Hyperbolic Haber sine, hyperbolic cosine, minus 1 over 2. The Haber cosine, the length of this segment divided by 2. Yeah, not much to say here. The x secant, finally, we have something kind of interesting. Round segment over here is the x secant. Has a very cool abbreviation. It's just the reciprocal of the cosine minus 1. Very cool. Next we have the x cosecant. Okay, it's not interesting anymore. We have more co-functions. Anyways, it's just a cosecant minus 1. Next we have the chord, which is basically the base of an isosceles triangle formed by 2 radii. I hope you understood that. Anyways. Okay, it's defined using versine, more sine. We have sagitta, defined using more sine, of course. It's also very tiny over here. The hack over cosine. I hope I didn't butcher that. That's 1 plus a sine over 2, not very interesting. Next we have the antichord. This is the first one that you won't see on Wikipedia because the guy in the video made it up. Nice. We can define it using more sine. The cochord is literally just the chord, but the complementary angle. Yay. Anyways, it's also the absolute value of 2 sine, blah blah blah, we don't care. The anticochord, more cosine and more sine, more pi. Yeah, it's just the chord, but connected to the bottom point. Next we have the isochord. This is the one that I made up. I'm very proud. You actually take the midpoint of the chord connected to the center, you have an isochord. Its length is also equal to 1 minus the sagitta, can be defined using more sine, blah blah blah. We still need to define it for you constants and numbers before we move on to defining the amount of 4's. We need 1, 2, 1/2, e, and pi. Also, these are the operators that we're allowed to use. With this, we can map the other numbers. 1 is 4 over 4, 2 is 4 plus 4 over 4, 1/2 is 4 over 4 plus 4, and e is that abomination, and pi is that abomination, using the gamma function. Also, this is how we would take a square root of something, because we kind of got rid of that. Now, let's get started finally. Here we have sine, cosine, tangent, cosecant, secant, cotangent, inverse sine, inverse cosine, inverse tangent, inverse cosecant, inverse secant, inverse cotangent. Yeah, that was a mouthful. Next up we have hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cosecant, hyperbolic secant, hyperbolic cotangent, inverse hyperbolic sine, inverse hyperbolic cosine, inverse hyperbolic tangent, inverse hyperbolic cosecant, inverse hyperbolic secant, inverse hyperbolic cotangent. That's a lot of 4's. Next, we have the versine, the hyperbolic versine, the cosine, the coversine, the hyperbolic coversine, the cosine, the haversine, the hyperbolic haversine, the havercosine. And finally, we have the x-secant, the x-cosecant, the chord, the sagitta, the Hackover cosine, the antichord, the cochord, the anticochord, which is very long, and the isochord. And that is every function defined using 4's. This took me like several hours of my time. I hope you enjoyed the video. You can subscribe if you want. That's all I have. Bye.